In 1788, a nearly complete skeleton was excavated from the banks of the Lujan River near Buenos Aires and shipped to Madrid, where it was assembled in the Royal Cabinet of Natural History and displayed for a public that had no framework for what they were looking at. The bones were enormous, larger than an elephant's in some dimensions. The claws were unlike anything on any living animal. The limb bones were so thick, so dense, so massively reinforced that naturalists examining them struggled to identify what kind of creature could have required that level of structural engineering in its skeleton. Georges Cuvier, the French naturalist who first formally described the animal from these bones in 1796, named it Megatherium americanum, the great beast of America. He identified it correctly as a relative of modern sloths. He also noted, looking at the bones, that whatever this animal was, it was built in a way that suggested something had been very, very difficult about its life. He was not wrong, but the difficulty was not what he imagined. Cuvier assumed, looking at the enormous claws, that Megatherium was a digger, that it excavated roots and tubers with those four-limb weapons. Later naturalists proposed it climbed trees. Others suggested it was semi-aquatic. For most of the 19th century and much of the 20th century, Megatherium was treated as a puzzle, an animal too large and too strangely proportioned to fit any existing template, classified as a herbivore by its teeth and left largely unexplained in terms of how it actually lived. What the fossil record has since revealed is an animal that was not a puzzle at all. It was a solution. Specifically, it was the most complete solution to the problem of predation that any large mammal in the Western Hemisphere ever produced. Megatherium americanum was not simply large. It was armored. It was armed. Its skeleton was engineered to a standard of structural redundancy that no predator on its continent was equipped to overcome. And it was capable, when threatened, of deploying a defensive capability that would have ended the life of almost anything that attempted to test it. This is why Megatherium was almost impossible to kill. Not because nothing tried, because the animal was built, layer by layer from the skeleton outward, in a way that made killing it a problem without a good solution. Start with the size, because size is the foundation on which everything else was built, and the size of Megatherium americanum is still underappreciated, even by people who know what it was. A fully grown adult male Megatherium weighed between 13,000 and 14,000 pounds, 6,000 and 6,400 kilograms. Some estimates push the upper limit towards 17,600 pounds, 8,000 kilograms for the largest individuals. Its body length, nose to tail, reached approximately 20 feet, 6 meters, when it rose onto its hind legs, which it did regularly as part of its normal feeding behavior. Its head reached approximately 17 to 19 feet, 5.2 to 5.8 meters above the ground. For context, the tallest living giraffe ever recorded stood 19.3 feet, 5.9 meters. Megatherium standing on its hind legs was a giraffe-sized silhouette. But where the giraffe achieves that height through extreme neck elongation on a body weighing around 1,700 pounds, 770 kilograms, Megatherium achieved it as a solid mass of muscle and bone weighing 8 times as much, balanced on hind limbs built like structural columns, and a tail thick enough to serve as a third support point. The femur. This is the bone that tells you more than any other what kind of animal Megatherium was. The femur of a large Megatherium specimen is among the most massive bones, relative to the animal's body size of any mammal in the fossil record. Not the longest, the most massive. The cortical bone, the dense outer layer of the shaft, is extraordinarily thick. The internal architecture, examined in cross-section, shows a density of trabecular bone, the internal lattice structure that determines how much force a bone can absorb before failure, that exceeds what equivalent bones in living elephants show. The Megatherium femur was overbuilt for the loads a slow-moving herbivore should have been placing on it. It was built for something else. For an animal that reared up on its hind legs and brought its full weight to bear on its hind limb skeleton repeatedly, and needed those bones to not fail when it did. The spine connects the femur story to everything else. Megatherium belonged to the order Xenarthrous, the same group that includes modern sloths, armadillos, and anteaters. The name Xenarthrous means strange joints, and the reference is to an anatomical feature unique to this group: additional articulations between the vertebrae, supplementary interlocking joints that do not exist in any other mammal order. In modern sloths, these Xenarthrous vertebrae provide the spinal rigidity that allows the animal to hang motionless from branches for extended periods without muscular effort. In Megatherium, scaled to an animal the size of an elephant and applied to a spine that had to support and transmit the forces generated by the forelimb, the Xenarthrous vertebrae created a spinal column of extraordinary rigidity and strength. The spine of Megatherium was not simply the structural core of a large body. It was an engineered load-bearing system, built to transmit the force of a forelimb strike from a 14,000 pound, 6,400 kilogram body through a rigid axial skeleton into the ground, and to do this repeatedly without structural failure. This is the structural fact that separates Megatherium from every other large herbivore in the Western Hemisphere. A bison has a spine. A mastodon has a spine. Both are strong. Neither has Xenarthrous vertebrae. The Xenarthran spine is an order of magnitude more rigid under torsional and compressive loads than the equivalent structure in any placental herbivore, because it is built with additional interlocking joints that prevent the vertebral column from flexing in ways that would dissipate force. In Megatherium, that rigidity meant that the force generated by the forelimb musculature was transmitted to the target rather than absorbed by the skeleton of the attacker. This is the engineering principle behind every effective weapon system. The weapon must be stiffer than the target. Megatherium's spine ensured that it was. This matters because of what was at the end of that forelimb. The claws of Megatherium are the feature that everyone who has ever seen a skeleton notices first and forgets the context of immediately. They are enormous. The third claw of the forelimb, the primary weapon, reached 12 inches 30 centimeters in length along the outer curve in large adults. In absolute terms, it is the largest claw of any known land mammal, but the raw measurement undersells what the claw actually was, because a claw is not a weapon in isolation. A claw is a weapon plus the arm that drives it, plus the body behind the arm, plus the skeletal architecture that transmits the body's force through the arm to the claw. The forelimb musculature of Megatherium, reconstructed from the muscle attachment scars on the fossil bones, was extraordinary. The deltoid, the muscle group that drives the forelimb forward and downward, had attachment points on the humerus that indicated development comparable proportionally to the most powerful forelimb muscles of any mammal we have ever studied. Multiple biomechanical analyses have placed the peak force output of a Megatherium forelimb strike at levels that exceed the striking capability of any living terrestrial mammal, including the grizzly bear, whose forelimb strike is sufficient to break the skull of a bison with a single blow. Megatherium's strike came from a body 16 times heavier than a grizzly, with a skeletal architecture specifically designed to transmit force rather than absorb it, and it terminated in a claw 12 inches 30 centimeters long. What that claw could do to another large animal is not difficult to calculate. What is difficult is finding a predator in Pleistocene South America or the North America that Megatherium's relatives occupied, that could absorb what the claw produced. The short answer is that none of them could. Not cleanly. Not without accepting catastrophic injury as the cost of closing the distance to attack. Smilodon populator, the South American saber-tooth, weighing up to 960 pounds, 435 kilograms, was the apex predator of Pleistocene South America, and it almost certainly encountered Megatherium. It almost certainly did not make a habit of attacking healthy adults. The fossil record has not produced a single definitive case of a large predator successfully killing and feeding on an adult Megatherium. That absence is not a gap in the record. It is the record telling you something. But the claws and the size and the spine were not the last layer of defense. They were not even the most remarkable one. the skin. This is where Megatherium stops being merely formidable and starts being almost conceptually resistant to the kind of attacks that Pleistocene predators could deliver. Embedded within the dermis of Megatherium and its relatives, a feature confirmed by the fossil record at multiple sites, were osteoderms, bone nodules, small rounded pieces of bone ranging from marble-sized to golf ball-sized, distributed through the skin in a mosaic pattern that created a flexible external armor over the body. This is not unique to ground sloths. Crocodilians have osteoderms. Armadillos, the living Xenarthrous most famous for their armor, have them. But in Megatherium, the osteoderms were present in a large-bodied animal that was already protected by size and claws, adding a third layer of defense to an animal that was already effectively unkillable by the direct approach. The practical implication of osteoderm armor on an animal the size of Megatherium is significant. A large predatory cat killing prey relies on specific points of vulnerability: the throat, where the jugular and the trachea are accessible through the hide; the base of the skull, where the spinal cord can be reached; the belly, where the hide is thinnest and the vital organs are closest to the surface. These are the targets that Smilodon's canines were designed to reach. These are the targets the American lion's throat grip was designed to access. Osteoderms do not cover every square inch of skin uniformly, but they make the initial penetration of the hide at any point significantly more difficult. And in the specific context of a predator attempting a throat grip on an animal that weighs 7 times as much as it does, the additional time and force required to get through armor-reinforced skin is time and force the predator does not have, because Megatherium was not standing still while this happened. Before the behavioral component, consider what a predator actually faced when it approached Megatherium. It faced an animal 8 to 10 times its own weight, an animal whose hide was reinforced with bone nodules that required additional penetrating force before any underlying tissue could be reached, an animal whose forelimbs terminated in the largest claws of any land mammal, backed by the most powerful forelimb musculature of any land mammal, transmitted through a spine that could not be destabilized by the force of the strike. A predator approaching this animal was not approaching prey. It was approaching a problem that had no clean solution. The behavioral component of Megatherium's defense is what transforms an impressive set of passive characteristics into something that makes the animal genuinely almost impossible to kill. Passive armor is useful. Active defense with passive armor deployed from a body of 14,000 pounds, 6,400 kilograms, is something else. Modern sloths are slow, famously almost comically slow. Their slowness is a function of their extraordinarily low metabolic rate, which is itself a function of the low caloric density of leaves, which is what modern sloths eat. Megatherium did not have a modern sloth's metabolic constraints. It was enormous, which means its basal metabolic rate was high in absolute terms, simply because metabolic rate scales with body mass. It ate vegetation of much higher caloric density than leaves, specifically the fibrous grasses and herbaceous plants of the South American Pleistocene, processed by a digestive system scaled for an animal of its size. Its muscles, as the attachment scars confirm, were massive. An animal with those muscles and that body mass were not moving at sloth speed. Estimates of Megatherium's locomotor capability, derived from limb proportions and bone cross-sections, placed its sustained walking speed at approximately 5 miles per hour, 8 kilometers per hour, and its maximum speed in short bursts at perhaps 10 to 12 miles per hour, 16 to 19 kilometers per hour. Slow by predator standards, not slow by the standards of an animal that does not need to run, because running is not its defense. Its defense was turning around. A predator attacking Megatherium from behind, which was the only tactically reasonable approach given the forelimb claws, was attacking an animal that could pivot on its hind legs and bring those forelimbs to bear faster than the attack timeline allowed for. Modern large sloths, when threatened on the ground, do not flee. They face the threat and they swing. The forelimb of a modern three-toed sloth, driven by a Xenarthrous spine and attached musculature, can deliver a strike sufficient to open a large wound on a human arm. Scale that response to an animal 30 times heavier, with a claw 12 times longer, and the defensive strike is not something any Pleistocene predator survived by being in the wrong position when it connected. Here is a detail from the fossil record that sits in the scientific literature without getting the attention it deserves. Isotope analysis of Megatherium bone collagen from multiple South American sites has produced results that challenge the assumption that this animal was purely herbivorous. The nitrogen isotope ratios in some specimens fall in a range that is elevated compared to what strict herbivory produces. Not dramatically elevated, not in the range of a dedicated carnivore, but elevated enough that some researchers have proposed Megatherium may have been an opportunistic omnivore, scavenging carcasses, or possibly even using its claws to access the flesh and marrow of large prey animals that had already died. The claws in this interpretation were not only defensive tools, they were also potentially used to open carcasses that other animals could not breach. A claw that can penetrate the hide of a large prey animal when driven by the fallen musculature of Megatherium was, effectively, a can opener for any carcass on the South American Pleistocene landscape. Whether Megatherium used it this way habitually, occasionally, or not at all, is still genuinely debated, but the isotope data exists, and it adds a dimension to the animal's ecological role that makes the picture of an enormous passive plant eater significantly more complicated. Understanding what Megatherium's defenses meant in practice requires understanding who those defenses were tested against. Not hypothetical predators, real ones, documented in the same fossil deposits, operating in the same ecosystems across millions of years of coexistence. The predators that shared the South American Pleistocene with Megatherium were not timid. Smilodon populator was larger than the North American Smilodon fatalis, with canines reaching 11 inches, 28 centimeters, and a body mass at the upper end of the saber-tooth range. The terror birds, the giant flightless predatory birds of the Forest-Rackidae family, had only recently been displaced from apex predator status in South America by the arrival of placental carnivores via the Great American Biotic Interchange. The short-faced bear had North American relatives that reached South America during the same interchange. These were serious predators, operating in a serious ecosystem, and the evidence of what they chose to attack, preserved in bone beds and fossil assemblages across Patagonia and the Pampas, show a consistent pattern. They targeted the available prey, the horses, the camelids, the giant rodents like Josephowatagacia manesi, the largest rodent in Earth's history. They targeted the animals they could kill. The absence of Megatherium in the prey assemblages is not total. There are sites where Megatherium bones appear with marks that may indicate carnivore activity, but the marks are inconsistent. The sites are few, and the evidence for successful predation on healthy adults is essentially non-existent. What the record shows instead is an animal that moved through a landscape full of apex predators and was largely left alone. Not because the predators did not notice it, because the calculation run by animals that survived by making accurate assessments of risk and reward consistently returned the same answer. The potential caloric reward from a successful Megatherium kill was enormous. The probability of a successful kill against an armoured, clawed, 14,000-pound, 6,400-kilogram animal that could pivot and strike faster than the attack timeline allowed was low enough that the expected value of the attempt was negative. The predators were not being cautious for aesthetic reasons. They were being accurate, and accuracy in a world where a single serious injury could mean starvation was survival. The question of what ended Megatherium is not simple, and the simplest version of it, that humans killed it, is true but incomplete in ways that matter. Megatherium americanum was extinct approximately 10,000 years ago at the end of the Pleistocene, as part of the broader megafauna extinction that swept the Americas. The cause, as with most Pleistocene megafauna extinctions, involves a combination of climate change and human hunting pressure, with the relative contribution of each factor still contested. The climate shifted. the plant communities Megatherium depended on changed. This was a pressure the animal had survived in previous interglacials, and probably could have navigated again. What was different this time was the addition of human hunters with projectile weapons, coordinated hunting strategies, and the ability to target the specific vulnerabilities that the animal's natural predators had correctly identified as insufficient compensation for the risks of direct attack. Human hunters did not need to attack Megatherium from the front. They did not need to close to claw range. A spear or an atlatl dart launched from 30 feet 9 meters could penetrate the hide between the osteoderms, could reach the organs that the armor did not fully protect, could wound an animal that no predator could wound at all without accepting a high probability of dying in the process. The animal that had been almost impossible to kill by every biological predator in its ecosystem was killable by something that attacked from outside the range of its defenses. Not easily. Megatherium was still dangerous at close range even wounded. Accounts from sites with evidence of human hunting of large ground sloths suggest the process was long and required multiple hunters and multiple strikes. But it was possible. And possibility, repeated enough times, is extinction. The last Megatherium died in a world that had been trying to kill it for millions of years and had mostly failed. The saber-tooths had failed. The short-faced bears had failed. The terror birds had failed. Every biological predator that shared its landscape across the millions of years of its existence had looked at what it was, run the calculation, and chosen something else. The armor held. The claws were not tested to their limit by anything that lived alongside it. The Xenarthrous spine transmitted its force without failing. And then something arrived that did not need to be within claw range. There is a detail about the Madrid skeleton that does not appear in most accounts of it. The bones are so dense, so massively constructed, that when the skeleton was first assembled and researchers attempt to calculate the animal's weight from its skeletal proportions, they underestimated it significantly, because they were using scaling relationships derived from animals whose bones are not built the way Megatherium's are. The bones themselves are heavier per unit volume than equivalent bones in modern large mammals. The density that made them so resistant to the forces the living animal generated also preserved them so completely that they arrived in Madrid looking not like fossils, but like bones from an animal that had died recently. 230 years later, they still communicate the same thing to anyone who stands next to them. The skeleton in the Royal Cabinet of Natural History in Madrid is still there. The one Cuvier described in 1796, the one that puzzled naturalists for a century, the one that revealed, slowly and imperfectly, the animal it had once been. It is one of the most complete large mammal skeletons in the world. You can look at the femur and understand why it is so thick. You can look at the forelimb and trace the muscle attachment scars and understand what drove those claws. You can stand at the base of the skeleton and look up at the skull 12 feet, 3.7 meters above the floor, and understand, in a way that no description fully conveys, that this was not a large animal in the way that most large animals are large. It was large in a different way, comprehensively, purposefully, as if size itself had been deployed as a strategy, layered with armor and weapons and structural engineering until the result was something that the biology of its world had no answer to. Almost no answer. Almost impossible. The difference between almost and completely is 10,000 years old, and it has a human face.